All right, up next, we've got Bob Patti. Bob's president of NHanced Semiconductors. Throughout his career, leading several organizations and successful startups, Bob has spearheaded cutting-edge development of 3D and 2.5D integration technology for the demanding compute applications of high-energy physics, medicine, automotive, and the military, among many others. Today, he's going to be presenting on his perception of a new reality where KGD is impossible, and the need to embrace this new reality with new design techniques in the areas of repair and redundancy as needed. So take it away, Bob.
Thank you very much. And my thanks goes out to MEPTEC and IMAPS for inviting me. So by way of background, NHanced does bleeding edge advanced packaging. And the concepts behind known good die are great, but as we see them extending into the future, where we see devices today which have tens of thousands, hundreds of thousands, or even millions of interconnects, this becomes increasingly difficult to determine what is a known good die. So instead, we look for proving and sorting out die that we know are bad, and the other ones we're assuming are probably good, but we want to figure out, how do you get yield out of this? How do you make this more cost effective? And we believe the methodology is you design for repair. You build in redundancy and you screen that your repair and redundancy is effective, and you can measure this in your ultimate product quality and yield. Well, how did we get here? And we all know, we can argue about when the end of Moore's law is or was, but we have lots and lots and lots of graphs from lots of industry pundits, and I'm among them, that says that Moore's law is failing us. And you know, it's not a function of can we build smaller devices. It's really a function more of the cost effectiveness of doing this, and how do we move on from here. Another thing that's driving a lot of where we're going these days is the Internet of Things, more and more sensor devices. And these sensor devices drive more and more exotic technologies, different materials, many different types of devices. And a lot of these are fundamentally incompatible. Even if you wanted to build an SoC, that would contain everything, it would become virtually impossible to integrate all the different types of technology. The obvious case in point today is we don't integrate DRAM with our GPUs. It's an absurd process combination. Instead, we build multi-chip modules, we build things on interposers, we're moving to chiplets, and that allows us to overcome this reality. And it is being driven harder and harder by the Internet of Things and sensors. So what is advanced packaging? Let's try to define what I'm talking about. Well, first of all, advanced packaging typically requires TSVs. Not always. You can do 2.5D, although 2.5D is usually on silicon or glass interposers, or perhaps even organic interposers, but all of those certainly have some form of via in them. Packaging really spans a very wide range of things to talk about. On the far left-hand side, you have the quintessential multi-chip modules, which have been built for 40 years. You have multiple die, they're bumped and flipped today. They used to be wire bonded. At the opposite end, you have, wafer fab. And wafer fabs, you can get hundreds of millions or billions of interconnects per square micron, or per square millimeter rather. And certainly we've seen demonstrated by IBM years ago, and much more recently by ST Micro and others, doing monolithic multiple layers of interconnect. And Skywater is doing this now with ReRAMs and carbon nanotubes. So advanced packaging kind of sits between the very high-end fab processes and the lower-end packaging processes. You're applying wafer fabrication processes and technologies to what has been typically packaging goals. And when we do this, we have many, many different alternatives when it comes to the advanced packaging technology. At NHanced, we do a lot of 2.5 and 3D integration, typically with hybrid bonding technologies. They often incorporate silicon interposers, sometimes, active interposers or active silicon circuit boards, some people call them. You're mixing R's and C's. When you drive the length of interconnect down, you make things faster and you reduce power. Interconnect is responsible for the vast majority of power consumption, and it limits the speed at which things run today. So the further you can drive down that wire, the higher performance you can get out of a device. This is an alternate vector to Moore's law. How can we continue to deliver Moore's law type improvement to our customers and the end customers who consume the cell phones and TVs and cars in the world without the benefits of the shrinking geometries? And advanced packaging is really a methodology to do that, probably for the next decade. A key constituent of this next advanced packaging leap is the interposer. Typically, they're built of multiple layers of interconnect. You have a through silicon via. This can be made today out of glass. That's a promising technology. And it allows you to do things at finer geometries than you can typically do with organics.
Bob, what's your take on active interposers, and how active does the active interposer have to be before we just call it 3D?
Yeah, it's once you get an active interposer, it's probably at the edge of 3D. And active interposers are problematic because of the cost. It's like building very large die, even if you build it in older technologies. So I would say that active interposers are probably not a good idea. But let me put something else out there that we've been playing with, and that is, instead of having active interposers, we simply go to like glass interposers, or you could use silicon, and instead use chiplets to stitch together and do the things that you would do on the active interposer.
Okay.
So you get the benefit of a quote unquote active interposer, but a cost structure that's more like a passive interposer. And the key to that, of course, is that you can put down small chiplets. I'll do a shout out to Acceloprint. I think their technology would be a good mechanism, the stamp printing, stamp transfer, to put down very, very tiny buffer chiplets and repeaters and those type of things on top of completely passive interposers. Once you start adding transistors into an active circuit element or into a interposer element, you probably, it's a very difficult economic trade-off. So hopefully I answered your question. So at NHanced, this is the bleeding edge of technology, at least the bleeding edge of what I can show. This is several years old. It was done at Tezeron. NHanced is a spin out of Tezeron. This was an 8-layer wafer stack. It has 80 layers of copper interconnect. It gives you a scale of the technology. I can tell you that the bleeding edge for us today, we have a customer that we build a 20-layer stack for, with 200 layers of metal interconnect. And we get in very low volume yet, I want to make it clear, but we're seeing yields between, I'd say, 70 and 80% on that 20-layer stack. So I would say, take what I say.
Bob, sorry.
Yes.
But when you say that yield, that's yield after repair or yield prior to repair?
Actually, that is, in this case, it's prior to repair, but the types of defects that we get are usually catastrophic and they're not repairable for that particular device.
Thank you.
And I want to point out that the technology that we're practicing is ahead of the curve. We do rock breaking for folks. The fab that we had has done rock breaking for building cameras that most of us have in our cell phones. It isn't the type of thing that Enhanced will run in high volume production. Our definition of high volume is 10,000 bonds a year. That's a lot. But we have things that have gone to commercial production and are running today that run in tens of thousands of bonds per month. So this is what's going to happen. So I'm trying to present a scenario of what the future looks like and a methodology to really deal with what I'm presenting. You know, what I'm showing you here, how do you repair that? You're not going to take it apart. You need a fundamentally different methodology. Here's another example, 5.5D systems. These are 3D devices. It's a 3D memory stack, an interposer on the back of it, and then processor die on top of it. And of course, we use GelPack. That's one of the sponsors here. And you know, they package the world's most expensive devices, which these are. The direction that ultimately what we're trying to solve in a lot of cases in the high performance computing area, this is a cartridge processor. It was a concept and unfortunately didn't get a lot further than this, but it shows you where the direction is going. It's very similar in concept to the Moonshot program that HP did with their cartridge processors. It was put forth as one of the packaging alternatives for exascale machines. You have basically devices which are, you know, the size of 3x5 cards that now dissipate 1,000 watts and have 1,000 pieces of silicon in them. They become almost impossible to repair. Okay, so all this advanced packaging, it solves all of our problems, and that's great. So where are the fatal flaws? Well, first of all, we have lots of choices in what we define as advanced packaging. There's the wafer to wafer, the stack, like I've just showed you, all the way down to package on package. As you move from the semi-monolithic or polylithic 3D type solutions to POP, there's increasing cost per connection. And that seems almost counterintuitive, but keep in mind that when we have wafer stacking, it's not uncommon that we could have 100 million to 1 billion connections per wafer. So while POP may only cost a quarter to do, it's only putting together perhaps a couple hundred connections. Or in the case of like flash memory, it's probably less than 100 connections per layer. As you go, you know, up the scale here to 3D, you have increasing complexity. And while it drives down by orders of magnitude the cost per connection, it certainly drives up the NRE, and it drives up the need for product planning and how are we going to do test. Another, you know, blessing and curse is the mixed material opportunities that we have. And probably the most important thing I want to point out is the CTE challenges. The temperature expansion differentials between the materials are ultimately the failure mechanism in what we see, as we see it, it is the failure in most of the parts that we see. As you get into very complicated structures, it is how can you keep the devices from tearing themselves apart as they go through thermal extremes. And this almost, adds into the shift left that Dave was talking about. Test, where do we do test? If we test in all the possible places, it adds a cost burden, and you have to very carefully assess where this is going to be. Because if everybody does all the tests at all the stages, you add significant cost to a product. I'll give you a case in point that is almost a worst case scenario. In past efforts that we had done, we built detonators for commercial explosives. It's a high volume device. It's disposable. It needs to cost next to nothing. The die content on it costs less than a nickel. The cost of testing that die was on the order of 3 or 4 cents, almost basically the cost of the die. And as you test it, can cause failures. That's very true as we get into more advanced, smaller interconnects. So there's this incredible trade-off. The complete manufacturing cost of this 2.5D device was $0.25. So how do you do this cost effectively and deliver very high quality? And I will point out, these were detonators. Bad things happen if they go off at the wrong time. And in this case, we assessed that the most cost-effective mechanism was to do no die level test. You simply, they sampled a handful of die on the wafer to determine where the device is binned. They did complete assembly of the 2.5D modules, and they did exhaustive final assembly test. Because the most important thing was that the device worked after it was all put together. And the incremental cost, it made more sense. Now, I'm not saying that that is, my shift right is not to contradict what Dave said, but rather you need to assess what you're doing and what is the most cost effective for what you're building. There is no one size fits all in this next generation of advanced packaging. So we find in the devices we build, we do significant planning with our customers. You have to evaluate where the failures are going to be. We are using new methodologies to deal with extremely high pin counts. We certainly, in the devices that we design, we have significant self-tests built in. We have deep embedded visibility, and we have to build in alternatives to speed test. You know, one of the problems with die probe is how do you exercise a 25 gig SerDes on every die, especially if you have hundreds of SerDes per die. The noise that you have in a test environment at die probe pretty much makes it impossible to get a good assessment that you've done everything right, or that the die is doing everything right. So what can you do to assess these high-speed interfaces and other high-speed circuits at the shift left early in the process? And of course, I'll harp on it, you know, more in the coming slides. A lot of it is about how do we do self-repair, self-redundancy. So we believe the future is chiplets. That is how we're going to move forward. I think I would probably not find very many people who would argue with that today. Certainly the AMD folks who are on the phone call here, Mike would agree that AMD is moving that direction. In our business, we don't build enough of any device to get statistical information. We build parts for satellites and space devices. I like to say it's really expensive sending a repairman to Mars. So we have to figure out, first of all, how can we get statistical reliability data when you build 20 parts? a lot of what we're building, you can't inspect. Visual inspection is in the rear view mirror. You know, X-ray inspection is desirable, but even X-ray inspection can't probably see everything that we would like to see. You know, I'll be down at the last line there. Probing causes damage. If you're building a module with 1,000 chips in it and 1 million interconnects, the probability of you causing damage by your test is relatively high. So one of the things that we've done in the past is we've built these memory stacks, and I'm going to point out just a couple of specific cases of how we here have analyzed and are doing tests differently. And one of those is memory, and I'll acknowledge memory is the easiest thing in the world to make redundant. I have a friend at Micron who likes to say, you know, if you're getting prime die at the end of the line, those are die that don't require repair, you're just not trying hard enough. So all memory today is repaired. And when we go into 3D, we are putting these all together. So I don't have, putting them all together permanently. I don't have the ability to go back and swap these die out in a stack. And HBM suffers from very much the same kinds of problem. Going back in and trying to repair an HBM stack is a non-starter. You just simply throw it away. So how can I get, you know, multiple 9s yield, especially in an end finished device? And that is that we do repair redundancy along the way. And at the end, we're able to repair the memories after the assembly is complete. So we have pushed all the way to the right the final repair of the devices. And an interesting anomaly of the way that we do repair and redundancy is, in our case, because we get more and more repair elements as we add memory in the stack, the yield goes up as we make the die bigger. It fundamentally runs the opposite direction of normal die yield. And this is a key to how we move forward. You have to look at the problems in a very different holistic manner to see how the world, to really get the benefit and the gain and pass this to the customer at a reasonable cost. One of the other things that we commonly build are networks on chip today. And, you know, we have our own protocols, and there's about 1 billion of them out there in the standards that people are working on. And the nice thing about doing things with 3D on chips, or networks on chip rather, is that you can do the same kind of things as the internet does. The internet is very reliable because if a node went down in the middle of my conversation here, all of you might notice a little frame skip, but it continues to work. And that's because the internet has the capability of rerouting. You can apply this technology, this technique, to what happens on chips. And I will just mention here, by the way, I think that AI will help us do some of this in the future. I think that we will have very sophisticated modules that all of us will be manufacturing within the decade. And I doubt the modules at the end of the line will all be identical. In fact, they will all be somewhat different. And I would state today, probably the GPUs that we all buy with the HBM memory steps, in reality, those are all different because the memories on every one of those devices has been repaired differently. So extending this repair and redundancy concept, today processor manufacturers typically have spare processors on their die, and that's so that they can yield and sell almost all of their product. We can do smart interposers. And as I stated earlier, I think we want to do that with a passive interposer and the smartness applied to the top of it. But having intelligent power control so that you can effectively mitigate binning issues. You can have programmable routing. HBM memories have spare I/O lines that can be used for failures in interconnect. It could be a failure on the die in the I/O, either on the processor or on the memory device, or it could be a failure on the interposer or anywhere in between there. You can use FPGA-like repair kits. Any of you who are on the phone call who build sophisticated die know that we build repair kits into chips all the time, so that we don't have to do all layer mask changes when we find out that we needed an inverter on the signal. Instead, we have these spare parts. We can go in and in metal masks, in the case of custom chips and ASICs, we can make a patch. We can use the same fundamental technique to apply patches to the next generation of chiplets. And as I already mentioned, the redundant I/O like an HBM. I'm going to touch on just briefly, I think, a very related topic here, and that's reliability. And as I gave the example earlier, how do we establish reliability when we're building a dozen of something? And even if you're building hundreds or thousands, it's very difficult to get enough statistical information to say what is the quality of the process you're running, especially if it involves many different techniques for assembly. What we want to know and what our customers want to know is this device reliable? If I'm building something that's going to go into outer space, I don't care what the statistical yield really is. I want to know whether this device works, because the repairman isn't going to go change it out if it fails. So our hypothesis is, can we measure the quality of an assembly and therefore infer the reliability of the device? Our plan, and what we've implemented at least in a handful of devices at this point, is by building on JTAG, we can put in electronic verniers and via change temperature sensors, as well as really the same kind of process control monitor structures that we typically do in at wafer level probe, build them into the 3D assemblies. Most of the failures we see, and I said this earlier, have to do with the assembly process. You know, I have good news. The known good die today, a lot of them are pretty good. The problem is when we start putting lots of these together with very fine pitch interconnects, and they're subject to different coefficients of thermal expansion, that's where they fail. Did that bond work well enough? Was the solder joint good enough? Was the alignment good enough? By looking at this data from each device, and these can be done below the visible spectrum. You don't have to see it to measure these things. We can validate the quality and therefore the reliability of this unit. And I'm just going to finish up here. I borrowed these pictures from Eric Marinson from IMEC. And those of you who are in 3D probably know Eric. This is something that they were working on, and we think it is the right answer. You can build on the IEEE standards for JTAG testing, adding in the analog capabilities to measure process control monitor information, alignment information, and that helps you prove the quality and therefore the reliability of this particular device. And in low volume, this is a requirement. I think that as we move to more sophisticated devices, and as it goes into high volume manufacturing, this is going to be an important facet of making sure that the product shipped in high volume is going to have the lifetime and customer reliability that is demanded by the consumer. And with that, I'll close.
Thank you very much, Bob. So there were a couple questions that were kind of answered off to the side. I'd like to get your take on it, on one of them at least. One of the questions kind of requested is there a max speed or frequency that you believe silicon interposers, the TSV within silicon interposers is going to be limited to?
Fundamentally, the answer is no. You have to plan for it. One of the issues with silicon interposers today, most of them, especially the high volume commercial, are using the last few layers of a 65 nanometer process, or at least something close to that. And that gives you a speed limitation because the RC time constants. You can make those layers thicker. For RF interposers, I know that we manufacture up to 10 micron thick copper. That is high enough that you can carry, you know, small tens of gigahertz type signals. So fundamentally, you can overcome it. You need to be cognizant of these things. If you're trying to get a 25 gig SerDes signal, you know, 10 millimeters across a silicon interposer on a 0.9 micron thick copper trace, and then down to a TSV, you're done. It ain't gonna work. Yeah. You use your entire link budget before you ever leave the interposer. This is why you need to tune the interposer technologies. We build these thick copper interposers today. I think other people will do them in the future as we have higher speed interconnect. You know, the advent of high-speed photonics is probably going to, the good news is it'll alleviate some of the problems off the module, but it will probably drive the modules to needing thicker copper interconnect just to get the signals to the transceivers.
Okay, thanks. And so one of the things that you had mentioned is that, you know, HBM does have cell repair, it does have IO repair. I think you're focused more on building ubiquitous repair as you move up the stack so that any die can rely on any other die's repair, which is something very different than HBM. HBM, you can only repair certain banks within certain dies given the, and so is that you're saying design needs to kind of put this repair in a position where I've got an SRAM over here, I'm stacking a die, that guy over there, this may die and I might not have enough repair for it, but if I put another one on, I might be able to use his. And so that kind of creates this switching network.
Yeah, and there's a continuous spectrum here of repair. And I'm certainly not implying that every device is going to have everything repairable forever. You're going to, there are, as a designer, I need to evaluate what are the most likely things to fail, and what is the most bang for the buck. If I have 16 SRAM chiplets, it might be worth putting down a 17th and putting a MUX in there so that if one of the 16 fails, I swap it in. If I have one SRAM chiplet and I can do some repair redundancy on it, I probably am not going to put on a second one just in case. There's not a single magic bullet. We saw how chip designers and package designers went from completely separate encampments that never spoke to each other to now they have to work together all the time.
Right. And on that note, do you think? Sorry, go ahead.
Yeah, well, I was going to say, and I think test is going to be invited to the party, so that rather than, you know, here's what we're building, you guys go make it yield now. It's got to be a much more interactive, and the data about what is failing. So, and we're going to learn, and one of the things we try to do is if we're building this next module, we look over our shoulder and say, what went wrong in the last one? What was the yield problem? What was the reliability issue? How can we change this next one? What statistical data did I get that I can now apply to my next generation?
And in that vein, do you believe that there should be some way to feed the generalized suggestions back to EDA tool vendors so that they can make recommendations as people are designing IP, and say, hey, you forgot about this, or don't forget about this concept. You're in a 3 nanometer process. You're going to want more of that.
I think that that's an evolution, and I do think that it is one of the areas for AI-like systems, expert systems, to help us, where it can sift the data. One of the really good things about AI is its ability to recognize patterns. And what we're talking about is a really, really sophisticated pattern. As I put together these different technologies, you and I are not going to look at it and say, geez, this is actually kind of matching something that was built 3 years ago, and we know that this was the failure mechanism. But an AI, an expert system, can look at it and say, there are similarities here. Hey, you might want to add some additional test or add some additional redundancy, or per what Dave was saying, maybe we need to do these kind of tests early on so we're not throwing so many of these modules away.
Bob, you mentioned CTE a couple different times through this presentation, and it occurs to me that the thermal situation changes over time. How do you think about repair once or repair often, repair once and forget? I don't know.
People are really uncomfortable about repair often, but it's what we did in the memories when I was with Tezeron. We did continuous repair. We had a microprocessor. We would watch for failures in time and make in-time failure repairs. We'd select different rows and columns. I think that's a requirement. We today, it was mentioned yesterday, the gentleman from NVIDIA was talking about the 50-some billion transistors they have in their GPU, ignoring the billions and billions more, or hundreds of billions and more in memory. That's part per billion failure rates already. They're probably at 1 part per trillion on a GPU module already. We don't build things that are that good. We certainly don't build them that are that reliable. So I would say to the folks out there, you can fight against this trend, but it's shaking your fist at the tidal wave. We are building things that are well beyond the reliability even of semiconductors. So the sooner you get on board with the concept of repair redundancy in life management of devices, the better off you're going to be, because it's going there whether you want it to or not.
By the way, devices are starting to wear out also.
Yeah. I saw a headline about that little note that deep submicron devices don't last as long as they used to.
Okay, we are just over time. I wanted to thank you very much, Bob. Thank you, Dave. Thank you, Bernice.
Also thank our sponsors once again. Our diamond sponsor, ASC, providing design, assembly, tests, materials, and components, logistics services to the electronics ecosystem through their different entities. So thank you, ASC. Thank you, Advantest, global leader in ATE, doing the heavy lifting of the testing to make all these advanced technologies available and reliable. To GelPack for solutions that allow material handling, both in fab and transport of very valuable devices. So thank you also to GelPack. And lastly, thank you to the Mullbauer Group in terms of factory automation and material handling. So thank you for sponsoring this event and making it possible. I want to remind everybody that the final session is tomorrow morning, Friday, September 18th, from 8 to about 10:30 a.m. Pacific time. We'll talk about solutions in particular. Your Zoom link that you used today is good for tomorrow. You'll also get a reminder. And with that, but I thank everybody for joining us today, and I wish you a good rest of your day and look forward to having you join us tomorrow. Thank you.